So I think this is kind of a neat lesson that it's pretty math theory intensive, but there's not a lot of actual math that you're going to have to do. Um, the idea is, what can you actually put together to make a triangle? What lengths can you put together? Can I put together a little segment about like this, another little segment about like this, and one that's as wide as my arms? There's certain parameters that you have to fall into for your shape to actually form a triangle. And that's what this idea is here, this thing called the triangle inequality theorem. Now, that sounds way fancier than it really is, but this is kind of the important part. What the inequality? What does it take for the numbers that are the measurements of the sides of a triangle for them to actually work as it would? Like I said, you can't just slap any three sticks together and make a triangle. It has to be done kind of in a certain way. I can't have two little ones and a gigantic one and it work, or I can't have, two gigantic ones and a teeny tiny one and it work. It really kind of all depends. And the measurements actually have to be within a certain range of one another. So the actual triangle inequality theorem says if I take any two sides and add them together, that has to be bigger than the third side. Now, if you take any two sides, that actually gives you these three different statements here. I think that we can kind of narrow that down and get rid of this and look just at the two smallest sides and compare it to the biggest side. So if I were to take these, this segment here that's, like let's say that's 10 centimeters long or whatever. The units don't matter. It's the numbers. And I were to try and build a triangle with a segment that was, say, 2 centimeters and one that was maybe 3 centimeters. I couldn't actually close that and make it a triangle. The two shorter sides wouldn't come together in a peak because together they're smaller than the third side. Specifically, they're smaller than the biggest side when I put them together. So what I'm ultimately doing is I'm comparing the two small sides to the third biggest side. So let's say if I change these numbers here, what if I made this, I don't know, let's say, make this one a little bit longer. Let's say this one's 7 and this one is, say, 5. When I start bringing those two pieces together, they're actually going to touch and come to a peak and make a triangle, because when I add 7 and 5 together, that is 12. That's bigger than 10. Don't get hung up on which way the sign's pointing here. The big end of it, the open end of it, should go towards the bigger number. Okay, so 7 and 5 together is bigger than 10. So that'll actually form and make a triangle. Now let's go back and change this number here, and let's make this side shorter. Right? What if I went back to when this was 2? Right? That 2 and 5, they're not going to come together, and they'll just kind of, almost like a hinge, the door will close and you won't be able to come together and make a peak as a triangle, because when I add those together, 2 plus 5, that's actually less than 10. So I think we can pretty safely get rid of the statements that compare the big side to the little side. We need to be comparing the little sides together to the big one. So what I want to do now is try and figure out what a possible third side could be for a triangle if I know two of the sides. So like we were talking about just a little bit ago, you can't just have any three lengths and then work in a triangle. So I'm going to give you two. You're going to try and figure out the third. Now, what you have to try and get your head around is that the side you're trying to come up with could be the smallest one in the triangle, and it could also be the biggest one in the triangle. And I want this triangle inequality to work on both ends of that. So going into this, we need to kind of have in our head, okay, what's the smallest one that'll work with 6 and 11? And what's the biggest one that'll work with 6 and 11? And I want that when I add the two small ones together, that it still be bigger than the biggest one. So we're kind of limited. There's a smallest number that will work, and there's a biggest number that will work. And our possible sides can be everything in between, right? I can't be too small and I can't be too big, but there's kind of like a just right spot where they'll work. So the way this is going to work out, I need a number that I can partner up with 6 that will just be bigger than 11. So the easiest way to do this, and I'm not trying to oversimplify it, but the easiest way to do this, if I were to take 11 minus 6, that would give me the smallest possible value. Come on now. That would give me the smallest possible value that doesn't work. So anything bigger than 5 will work, because if I take 5 and 6 and put them together, that would just be 11 and collapse on itself. So anything bigger than 5 will work. Now the flip side of that is true. What if I'm looking for the big one? I want the biggest number out there that'll work for 6 and 11. Well, 6 and 11, if you make those the small sides, they'll just come together and collapse at 17. And I got that by adding 6 and 11. Now I want to stress, 5 doesn't work as a side. 17 doesn't work as a side, but anything bigger than 5 will work, and anything less than 17 will work. So like 5.5 would work because it's bigger than 5, but like 4.9 won't work because it's less than 5. So literally anything bigger than 5 and anything less than 17. So our range, our set of values, can be between 5 and 17. So long story short, you can subtract the 2 numbers I gave you to get the small value, and you can add the 2 numbers I gave you to get the big value. So over here on this one, to get the range, I'm going to subtract these guys and say 1 on the low end, and then add them, and it's 23 on the big end. And again, 1 doesn't work and 23 doesn't work, but everything between 1 and 23 does work.